Okay, guys. So last time we introduced the inner ear. We talked about that there is three parts to it: the vestibuli, the semicircular canals, as well as the cochlea. So we're going to take a look at the vestibuli to start with, and then we'll go through the semicircular canal and eventually the cochlea. So within your vestibuli, you have these areas of clustered cells that are called utricle and succulent. These two contain a specific type of sensory cells called hair cells. Now, the structure that you see both in the utricle and succulent are the same, and I'll go over that in just a minute. The main difference would be the way that they are positioned. So I just want to show you a picture of how they are located compared to one another. So again, we kind of looked at this. Utricle is on a horizontal plane, what you will see right here. And then succulent is on a vertical plane. It is important, as we'll learn in just a minute, why I'm talking about them in this sense. So let's go ahead and look at a very brief overview of what succulent and utricle functions are. So succulent, which is the one that is in a vertical plane, allows us to understand or detect what we identify as a linear acceleration and a vertical plane. Basically, if you're in an elevator and you're going up or down, that feeling that you get that you're moving up or down is created by the succulent. Versus when you are in a car and the car is moving or speeding forward or backward, that is in a horizontal plane. That acceleration is in a horizontal plane. That is measured by your utricle. So keep that in mind. We'll explain it in a little bit more detail. So utricle and succulent are contain these clusters of hair cells in an area called macula. Okay. Now, these hair cells have these tiny extensions. I'm going to show you this. These tiny extensions, here's my hair cell. They have this tiny extension called stereocilia. Now, a stereocilia is sitting in this gelatinous material, which you see in the light blue. And on top of that, densely packed right on top of that, you have a structure called statoconia. Statoconia is basically calcium carbonate crystals. And you can see kind of they shape like crystals, right? So what you have here, you have basically on top, you have quite a few calcium carbonate crystals or statoconia. That sits on top of a gelatinous material. And within that gelatinous material, you have these finger-like extensions coming off of your hair cells, these little tiny things, called stereocilia. Now, this structure, this gelatinous material, plus the statoconia, those crystals, they're called together otitis, okay? Now, why do we even care about that? Keep in mind, guys, what I'm describing is true for both utricle and succulent. It's just a different orientation in terms of horizontal versus vertical. So when you're standing, when you're just standing in a place upright, what you have is your otitis is pushing down on your hair cells. So this structure right here is pushing down on your hair cells. And as a result, you notice that basically you're standing up. Now, when let's say you tilted your head forward, okay, like as it's depicted in this picture, what happens is the gravity is gonna move those crystals, right? Your statoconia, those crystals are gonna shift, and that shift is going to trigger activity in the hair cells that are right here, right? So the shift of these crystals on the top, or your statoconia, causes activity in the hair cells. That activity is what gives you the sensation that, okay, I'm bending forward, or I am going back forward, or I'm going up or down. So now let's put this in perspective to the utricle and your succulent. Now, remember that the succulent is associated with your linear acceleration on a vertical plane, getting in an elevator, going up or down. So when you get in an elevator and you start to go up, right? What you're actually doing is you're, I should start with going down. So when you go down, you're plunging downward, right? You get that immediate feeling that you're moving down. The reason for it is because the otitis, that area on the top, no longer is pushing forcefully against what? Against your hair cells. And that shift that you notice, that shift that the crystals are not pushing on your hair cells, basically create the feeling that you're moving downward. Now, as soon as the otitis catches up with your receptor cells or your hair cells, then that feeling goes away. So let's say you're going down an elevator by, let's say 100 floors. The first 10 floors you notice, and then you basically go like, oh, I'm just standing still. Until when? Until your elevator is basically slowing down, right? So when it's slowing down, the otitis starts to press harder against your hair cells, right? Because when you're going up, right, the otitis is being pushed into your hair cells, right? So that increase is what you feel or get the perception that you're moving upward. Now, eventually, again, the movement equalizes between your hair cells and your otitis, and you don't feel that you're moving upward. Now, transfer the same information in terms of your linear acceleration in a horizontal plane. So when you're a car suddenly speeding up, for instance, the otitis is lagging behind, right? Because basically you're moving, but the otitis is trying to catch up with it, right? So that distortion that you notice basically tells your sensory neurons that you are speeding up, right? Or speeding forward. Imagine you're doing backward, right? Your otitis gets pushed into your hair cells, right? They get kind of like squeezed together, if you want to say that, and you get the feeling that you're moving backward. And again, that eventually reaches equilibrium and you don't feel that movement anymore. So it is important for you guys to understand how similar and different utricle and succuli are. The next structure we have are your semicircular canals. As I mentioned earlier, there are 3 semicircular canals, what we identify as the anterior one, the posterior one that sits in the back, and then the lateral one. The job of these is also very important. They actually measure what we identify as angular or rotational movement of the head. So it's not the movement of me going forward or backward or up or down, rather than the rotational. So let's put it in perspective. When we think about the anterior semicircular canals, the receptors that are in that area are going to motion or detect the forward and backward movement of the head. So imagine you're shaking your head, yes, right, forward and backward. That motion, you feeling that you're creating that motion of forward and backward, is detected by your anterior semicircular canal. The one that sits in the back, called the posterior semicircular canals, movement that it feels, that it detects the head movement side to side. So imagine you're doing kind of like the neck exercises when they tell you to turn your head and have your ear touch your shoulders, right? That tilting of the head, touching your shoulders, that's motion is sensed by your posterior semicircular canal. The third semicircular canals, which is known as lateral semicircular canals, is sensitive to horizontal rotation. So imagine you're shaking your head, no, side to side, right? That motion is monitored or detected by your lateral semicircular canals. So bring both the semicircular canal and the vestibuli together as important in terms of spatial sensations, right? Balance and equilibrium. All the movement that I've described, going up and down, front and back, forward and backward, right? Side to side, horizontal rotations. All of these is basically going to tell you where your head is located compared to your body. Now, at the ends of your semicircular canals, you have these enlargement called ampulla and I'll just show you quickly what the ampulla looks like. So these are the enlargement that you see at the end, called the ampulla. And these are, again, there's just the enlarged areas at the end. They do house equilibrium receptors, which can kind of, which is essential basically for spatial awareness. Couple of pictures, take a look at it. This is what we already described, so I'm not gonna go over detail again with them, but just kind of give you an idea of what these content look like in a different image. Same concept here. Quick note, guys, the data that is being collected regarding the spatial positioning of the head in terms of semicircular canals or your vestibuli gets collected by these branch of the nerves called the vestibular nerve. Vestibular nerve is the branching of a nerve or cranial nerve number 8, which eventually merge with the cochlear nerve. So it becomes vestibulocochlear nerve, as you can see kind of at the end of this. So let's continue. Internal ear, the next part that we have is the cochlea, which is basically the most important aspect of your ear, since the job of your ear is for you to hear. So cochlea is an extension of the vestibuli. It creates that kind of the pattern or the spiral pattern, which as a whole called the cochlea. At the center of the cochlea, you have what we identify as the cochlear duct, and that contains a spiral organ or organ of Corti. And I'll go into detail about this again. This is just kind of a quick overview. The organ of Corti contains hair cells. Hair cells are your sensory cells, and changes within these hair cells is what gives you the capacity to hear, okay? So if you guys recall what we talked about, the hair cells and the stereocilia of the hair cells for the vestibuli, you can kind of transfer some of that information over for these hair cells as well. Now, if you guys recall, when we were talking about earlier, and I'm just gonna show you a picture. Here is an open version of the cochlea. So kind of take that snail shell and unwrap it or unravel it. You have your bony labyrinth, that's the surrounding area, right? So this is your bony labyrinth in kind of that, again, peach color. Within that, you have that blue color, which is your fluid called perilymph, right? So that fluid inside here, the blue color is perilymph. At the center of this, you have that blue cavity, the green cavity that is called the cochlear duct. And if I ask you, what is the cochlear duct filled with? Your answer should be endolymph, right? Review this picture, guys, if you want to get an idea. If I do a cross section of this cochlea, this is the image you should see. And I'm just going to go back to show you what I talk about. This image. So again, bony labyrinth surrounded by perilymph, the cochlear duct, and at the center within the cochlear duct, you have your endolymph. Okay, so reviewing the name, if you're looking at your cochlear duct, and again, kind of going through this picture, right? The area that you see right here, where the oval window basically connects, right? Here's your stapes, the last ossicle. Here's the connection point, which is the oval window, and you have this kind of the area right here. Now, this area on the top originates from the vestibuli region, right? So this is called a Scala Vestibuli. So right here, this is number 1, and I'm just gonna kind of number it for you guys. Scala Vestibuli. A Scala Vestibuli, which starts with the oval window, goes all the way to the end, and then comes back as this kind of turnaround. Kind of think about it as two-way street. So this is a street that's coming back that ends toward the tympanic membrane, which would be somewhere here. That's your tympanic membrane. So this area on the bottom, which is still filled with perilymph, it is the continuation of your Scala Vestibuli called the Scala tympani. So this is your scala tympani. Again, if I tell you what fluid it is filled with, your answer should be perilymph. Now perilymph, a scala tympani ends with this area right here called the round window. Now, round window, this surface right here, is covered with a thin membrane. Sometimes it's called the secondary tympanic membrane. I don't need you guys to know that, but it is kind of good for you guys to understand. So why is this important for us? Let me explain this way. When you think about your sound or vibrations of the sound, we're saying that the vibration of sound comes through the external acoustic meatus, hits your tympanic membrane, right? Which causes the vibration of the tympanic membrane, the malleus, the incus, and the stapes, right? So stapes passes those vibrations through the oval window to your Scala Vestibuli. So this fluid basically starts to vibrate. Now here is very important, guys. As this vibration gets into this space, your fluid that is within this space cannot compress. So it's not like if you have the fluid and you introduce the wave, you can keep the fluid the same, right? Just because you're introducing something to it, it doesn't make it ability to compress. So those waves, those extra waves that are getting into your ear has to have a way to kind of be relieved. And that relief point comes from your round window. So kind of think about oval window brings all of these vibrations, it goes through as it needs it, and then anything that is extra, it comes up. I love the example your textbook or the metaphor your textbook has used. So your textbook describes it as a water bed, right? So if you sit in one area of the water bed, right, what happens to another area? It bulges out. Same concept here. If I'm pushing in by creating vibrations of the sound here, right, those vibration sounds need to go somewhere. So what are they going to do? They're going to bulge out through the round window. You push in one area, it bulges out somewhere else. Now, why is this important in terms of hearing? So for that, we need to go into more detail about your cochlear duct, your endolymph, and your organ of Corti, which is what we're going to focus on. So we already talked about oval window as well as the round window. So again, you're welcome to read this slide, but I like to describe it on the picture, nothing beyond what I've described to you already. So organ of Corti, which is basically sitting inside your cochlear duct. The area that is located, it sits on a membrane called the basilar membrane. And this is the basilar membrane, is the membrane that is separating the scala tympani from your cochlear duct or from your scala media. So you guys may get confused. So let me show you a picture. So here is a cross section of your cochlea. So take this, I'm gonna go back here. So imagine I've done this cross section. So I'm gonna see one membrane on top, one in the middle, and then one on the bottom right here, right? So 3 separate sections. So here is what you see. The one on the top, as you can see on the previous picture, is your Scala Vestibuli, right? The original one. And again, it contains the perilymph. You have the middle section, which is called the scala media or the cochlear duct, that contains endolymph. And then the bottom one, which is ending toward the tympanic membrane or toward the round window, is called the scala tympani, which is the continuation of the Scala Vestibuli, and therefore it does contain perilymph. Now, what you see here, and kind of enlarging this picture right here, this is referred to as the spiral organ or organ of Corti. So let me just write it down, organ of Corti. Where does this organ of Corti sit? It sits on this membrane right here, which is called the basilar membrane. If I specifically ask you what is the basilar membrane, it's basically the membrane between the scala tympani, right, and the cochlear duct, which is also a scala media. Now let's enlarge this picture and say, what is this organ of Corti looks like? So you have your basilar membrane right here. You have your hair cells right here. These are your hair cells, not the supporting cells, I should say darker blue color. They are categorized to outer and inner ear hair cells. I don't need you guys to know that as far as you know hair cells. Now here's a crucial point that you do need to know. On top of your hair cells, and you can see this kind of like your stereocilia sitting in there. So these little tiny things are your stereocilia. They are sitting on this membrane, which is a very firm membrane called the tectorial membrane. Okay, so basal membrane, right below it would be your scala tympani. This space that I'm showing you is your cochlear duct or your scala media. Within that, you have the hair cells, two categories, outer and inner. And these hair cells are firmly attached to what we identify as the tectorial membrane. So how does all of this come together to give me the ability to hear? First thing that happens is as the sound wave comes into the ear, it transfers through the external acoustic meatus, right? And then goes into your tympanic, hits your tympanic membrane, causes the tympanic membrane to vibrate, right? So vibration of the tympanic membrane. As tympanic membrane vibrates, it causes the vibration of the malleus, incus, and stapes, right? So these three bones are vibrating. Now, the vibration of the stapes pass through the Scala Vestibuli, through the oval window. And these vibrations are going to be passed to the cochlear duct. So the vibration from the Scala Vestibuli is going to be passed down to the cochlear duct. So what does that exactly do? So as your cochlear duct, any kind of distortion as a result of the vibration of the perilymph causes the organ of the Corti to be changed. How does that do it? The basilar membrane moves because of that vibration of the sounds that is passing through the perilymph. But at the same time, the tactile membrane, so the tectorial membrane that is sitting on top of your hair cells are going to stay still. So the bottom membrane is moving, and then the top membrane, which is your tectorial membrane, stays the same. This fluctuation, that movement versus no movement, stimulates your hair cells. Okay, so let me show you on a picture. So vibrations, as it passes through the cochlear duct, it causes the basilar membrane to move, right? But the membrane that is on the top, the tectorial membrane, stays the same or stays firmly in place. And that causes the stimulation of your hair cells in the middle. Do you need to know more detail than that? No. Of course, it is not as simple as I'm depicting for you here, but that's the level that I'm comfortable with you guys right now. Now, the stimulation of the hair gets picked up by these yellow nerve endings that you see right here, which eventually join together to form your cochlear nerve, which is the cranial nerve number 8. So, basilar membrane, tectorial membrane stays the same, hair cell gets stimulated. That stimulation, because these are nerve cells, gets converted to action potential, electrical impulses, that gets traveled up through the cranial nerve number 8 to your thalamus, through either your medulla oblongata or your pons. Again, it's more complicated than this, but that's all I want you guys to know. And that signal eventually ends in your primary auditory cortex, which is located in your temporal lobe. That is basically where you can hear the sounds by converting the signals into electrical impulses. Quick note, in terms of the ability to vibrate, sorry, I should say sound waves ability to vibrate your tympanic membrane. Typically, we say that tympanic membrane can be vibrated within the range of 20 hertz, which is really, really low, up to 20,000 hertz, or another sense, 20 kilohertz, if you want to put it. Again, these vibrations, depending on the level, they go through the ossicles and eventually through the perilymph. If you are dealing with high frequency or high pitch sounds, those sounds typically get passed through the cochlear duct and toward the oval window, closer to the oval window. Let's show you the picture. So here is basically sounds that would be higher pitch sound. Sounds that might be super low pitch are heard farther away. And sounds that you cannot hear, which is this arrow right here, basically are passed through without causing any stimulation. So, for instance, let me just give you an example. Let's say you're hearing a sound in 50 hertz, right? Your 50 hertz would be heard somewhere here, right? The vibration causes the cochlear duct stimulation or the organ of Corti stimulation, you hear the sound. I should say not 50, close to 20,000, I should say, like 18,000, let's say, which is really high actually. You would hear it here. If they are really low frequency, low pitch, you go farther back in this path. And if it's beyond your hearing range, it just kind of circles through the vestibular, Scala Vestibuli, and then a Scala tympani, and eventually exits through the round window. So keep in mind when you're studying this path, a few points. First of all, when you're talking about the cochlea, the hair cells are the main type of cells that are involved in creation or conversions of vibration of the sounds to electrical impulses. Organ of Corti is located within your endolymph, and it's located within the fluid endolymph and within a cavity called scala media, or also known as the cochlear duct. When we're talking about the path of the sound, we start with your auricle, external acoustic meatus, passing that to the tympanic membrane, your malleus incus stapes. Stapes is connected to the oval window. The vibration gets passed down to the perilymph within the Scala Vestibuli of the bony labyrinth. Depending on the vibration of the sound or the frequency of the sound vibrations, either again ranging between 20 to 20,000 hertz, you activate different parts of the cochlear ducts, organ of Corti, and the stimulation of these hair cells that are located in the organ of Corti get picked up by the nerve fibers that eventually becomes the cochlear nerve, which is cranial nerve number 8, and transferred to the temporal lobe for ability to hear. So that's about it for this lecture. Please guys focus on the 3 parts of the ear, know the specific function, know both the macroscopic and the microscopic anatomy as we talked about. Focus on the difference between the utricle and succulent, and then also the ability, the process of hearing through the cochlea. That's about it, guys.